Okay, everybody, we are going to do sections 9.5 and 9.6 together since they're both short. I've got my side door open today, so you might be able to hear the birds, but I'm finding them really encouraging, so maybe you will too, if you hear them. Anyway, moving on. Okay, so hypothesis test for standard deviation. So first we're going to look at finding the critical values of chi-square distribution, the test hypothesis about the standard deviation of a normal distribution. Finding the critical values of the chi-square distribution. So the hypothesis tests for the standard deviation are based on chi-square distribution. As we know, chi-squared distributions are skewed to the right, and the values of chi-squared statistic are always greater than or equal to 0. So there are many different chi-square distributions with different degrees of freedom. The figure below reminds us of several examples of chi-square distributions. So here we have with the degree of freedom of 1, degree of freedom of 2, degree of freedom of 3, or 10. Let me do that again. Degree of freedom of 1, degree of freedom of 5, degree of freedom of 10, degree of freedom of 20, and degree of freedom of 30. So the notation chi-squared sub A represents the value that has an area of A to its right. We consult table A4 to find the critical values associated with the chi-squared distribution. Finding the critical value of chi-squared 0.05 for chi-square distribution with 10 degrees of freedom, we look at table A4. The critical value is located at the intersection of the row corresponding to 10 degrees of freedom and the column corresponding to 0.05. The critical value here is 18 and 307 thousandths. Testing a hypotheses about the standard deviation of a normal distribution. The null hypothesis for a standard deviation little sigma is in the form of the null hypothesis is the standard deviation, which is going to be equal to the null hypothesis standard deviation. The test is based on the fact that if the null hypothesis is true, then the test statistic would be chi-squared equals n minus 1, the degrees of freedom, times our statistic standard deviation, all divided by the population standard deviation given squared, which is the variance, right? So this has a chi-squared distribution of n minus 1 degrees of freedom. Now they caution you this method of this section apply only for samples drawn from a normal distribution. If the distribution differs even slightly from normal, these should not be used. So to check to make sure assumptions are satisfied, we must have a simple random sample from a normal population. We're going to state the null and alternate hypotheses. We choose a significance level alpha and find the critical value using table A4 with n minus 1 degrees of freedom. If we have a left-tailed, then the critical value is going to be chi-squared sub 1 minus alpha. If it's right-tailed, it's chi-squared sub alpha. And if it's two-tailed, it's chi-squared alpha over 2 and chi-squared 1 minus alpha over 2. Step 2, we're going to complete the test statistic. And step 3, then we're going to determine whether to reject the null hypothesis as follows. Going to reject it if chi-squared is less than chi-squared 1 minus alpha. We're going to reject the right tail if chi-squared is greater than or equal to chi-squared alpha. And we're going to reject a two-tailed if chi-squared is less than chi-squared alpha over 2 or chi-squared is less than chi-squared 1 minus alpha over 2. So looking at an example, check the reliability of a scale in a butcher shop. The test weight is known to be 400 grams and was weighed 16 times. For the scale to be considered reliable, the standard deviation of the repeated measures must be less than 1 gram. The standard deviation of the 16 measured weights is 0.8 grams. We're going to assume that the measured weights are independent and follow a normal distribution. Can we conclude that the population standard deviation of the measurements is less than 1 gram? And we're going to use the significance level alpha equals 0.05. So we have a random sample from a normal population, so the assumptions are satisfied, and the null and alternate hypotheses are as follows. The null hypothesis is that the standard deviation is equal to 1 versus the alternate, which means it's less than 1. We have 16 minus 1, which is 15 degrees of freedom. This is a left-tailed test, so the critical value is chi-squared 1 minus alpha, or chi-squared sub 0.95, and that will be equal to 7.261. The sample size is 16, and the sample variance is 0.64. So the value specified by the null hypothesis is the standard deviation of the null hypothesis is given to 1. We compute the value of the test statistic using this formula given to us earlier, where we had the degrees of freedom times the sample variance all over the population variance equals 9.6. The value of the test statistic chi-squared is 9.6, and the critical value is 7.261. Now, since it's a left-tailed test, so we're going into the left, we reject the null hypothesis if chi-squared is smaller than chi-squared at 0.95. Since 9.6 is bigger than it, we do not reject the null hypothesis at the 0.05 level. So what we say is there's not enough evidence to conclude that the population standard deviation is less than 1 gram. We cannot consider the scale to be reliable. And again, notice the wording. We're saying there's not enough evidence to conclude that it's less than 1 gram. We are not saying for sure that it is equal to 1. We are saying there's not enough evidence to show that it is less than that. Now, from 9.4 or 9.5, you should find the critical values for chi-squared distribution. Use the assumption for performing a hypothesis test for standard deviation and normal distribution, and how to perform a hypothesis test for standard deviation of a normal distribution. Once again, I don't think I have to tell you, 3x5 cards, organize yourself, make a flow chart, whatever you think is best you need to do for preparing for this section and what tests you should do. Okay, we're going to go on to 9.6, which is a summation of determining which method to use, and this might help you. So we're going to determine which method to use when performing a hypothesis test, and how we're going to do that is figuring out which type of parameter we're estimating. So we're going to begin by summarizing the types of parameters about which we've learned to perform hypothesis tests. We have the population mean, we have the population proportion, and we have the population standard deviation or the variance. Notice these symbols, very important because it tells you whether it's the population or the sample. There is more than one procedure for testing a population mean, mu. The tests are z-tests and t-tests. So this diagram will help you select the appropriate test for the population mean. Is your standard deviation known? If that's yes, you're going to ask, is it greater than 30? If that's yes, you're going to use the z method. If that's no, Is the population approximately normal? If that's yes, use the Z method. If it's no, consult a statistician. So you can see this flow chart is very similar to the one that we used before. So if is the standard deviation no, if it's known, if it's no, then again you ask, is it greater than 30? If it is, use the T method. If it's not, then you're going to see if it's approximately normal. If it is, you use the T method, and if it's not, you consult a statistician. So these flow charts will help you a lot in determining which you should use. So you need to use them when you get stuck on your homework. You need to go back and take a look and use these before you search through all the rest of the pages. All right, so you should know how to determine which method to use when performing a hypothesis test. And that is it for section 9.5 and 9.6. We are now finished with chapter 9, and we are going to be moving forward to chapter 10.